Embedded systems cover a vast number of disciplines, of which we are going to focus on the microcontroller. So, this course is geared towards Cortex M microcontrollers, and such microcontrollers can be found in automotive, it can be found in robotics, wearables, drones. This is a learning thermostat. And on the industrial side, you can find embedded systems as portable power inverters or power inverters for that matter, which can have microcontrollers ranging from 8-bit to 32 bits. You have solar inverters, you have SMPS, and this is a programmable logic controller or a PLC. So microcontrollers can be found in all of these equipments, and they can range from 8-bit to 32-bit. There are other examples of embedded systems as well. For example, you could have printers, you could have medical equipments, you could have scanners, you can have so many things. You can replace the word embedded by dedicated. That is, whatever hardware and firmware that you have running on that particular equipment is only for that purpose. You cannot use that hardware for any other purpose. You cannot use it as a desktop. So it is only suited for the purpose at hand. So that is one definition of embedded systems. And for example, if a particular hardware and firmware is geared towards, say, doing a traction control in an automobile, it is dedicated to that functionality and it is specialized for that functionality. It is not like you have a desktop and you program something and use a general purpose operating system to design traction control. So that is going to have a lot of disadvantages. You will have to, for pure embedded systems, you will have to abide by a lot of constraints, for timing constraints and response times and power usage and many more things. So that is how embedded systems are distinguished from general purpose operating systems. And PLC, for example, is used for industrial control. So embedded systems is heavily used in control. For example, this traction inverter has a control component. It is a 3-phase driver, which also is a control circuitry for the motor. So this has logic for motor speed control, and it runs on a feedback loop. It might have multiple loops, and it might follow the principles of control systems. Same applies to even SMPS, PLC, solar inverters, anything that you see. Where control systems is not used to that extent, maybe an embedded watch or an MP3 player or a handheld scanner. The microcontroller family that we are going to look into is Cortex M4. And we are going to look into the Cortex M4 architecture in general, and then we are going to go into an ST based microcontroller, which is STM32F411, and we are going to program on that particular microcontroller. And the board that we are going to use is the Discovery board, which has a STM32F411 controller. So going ahead, Cortex M4, M3 and M4 processors are designed by ARM, and the Cortex M3 processor was first of the Cortex generation of processors, released by ARM in 2006. The Cortex M4 processor was released in 2010. Now, most of you will be aware of microcontrollers and processors. Now here we are entering the 32-bit domain, and those of you who have worked on 8-bit and 16-bit controllers prior to this will find this a bit different. This requires a lot of configuration and understanding of its subsystems. So the Cortex M3 and M4 processors use a 32-bit architecture. Internal registers in the register bank, the data path and bus interfaces are all 32 bits wide. The instruction set architecture in the Cortex M processor is called Thumb ISA or Thumb Instruction Set Architecture, and is based on the Thumb 2 technology, which supports a mixture of 16 and 32-bit instructions. Now, what is the prime difference between 8-bit, 16-bit and 32-bit architecture? what are the factors that are different between each processor? For example, if you talk about the analog to digital converter unit of a 8-bit and a 32-bit controller, they may be pretty much the same. So because say it's a 10-bit ADC or any higher bits, 12-bit ADC and so on, the ADC is the same, say for an AVR and an ARM. So there is no difference in the ADC. So what distinguishes the AVR from ARM? It is the width of the buses. That is the data bus here. So that is the bus or the connectivity on which the bits flow. Okay, is for ARM it is 32-bit. Say for AVR it is 8-bit. So here we see that in one clock cycle. So if you say all processors are run by clocks, so in one clock cycle you will have more data being processed by the controller. So one advantage we see of 32-bit architecture is it moves more data. That is one advantage of 32-bit architecture. Another advantage of 32-bit architecture is you can use a flat address space without any paging issues. For example, since this is the 32-bit architecture, it can address 4 GB of address space. Okay, because it's 2 raised to the power of 32. That is quite a bit of memory span that a 32-bit processor can address. And since it's 32 bits, for example, any in arithmetic operations. So for example, if you declare a 32-bit integer, say for example you declare unsigned int some value in C, if you declare the same value on an 8-bit controller, the 8-bit controller having an 8-bit data bus has to break up that particular data into multiple bytes. So if it's a 32-bit value, it has to break it up into multiple bytes, and say you are doing a multiplication operation between two 32-bit numbers on an 8-bit controller. The code size is larger because it has to write a lot of assembly code to make that happen. So if you are aware of 8-bit assembly code and you are trying to multiply say two 32-bit numbers, you will know how tough it is, because it has to run a lot of extra logic to multiply those two numbers. In the case of 32-bit, it happens in one clock cycle, because 32-bit means that number is saved in the register, and the arithmetic logic unit of this particular controller, that is ARM controller, is capable of handling 32-bit arithmetic. So if two numbers come in of each 32-bit in one clock cycle, that operation is done. So this is clearly advantageous. That is, for processing larger numbers and processing them quickly, we will need 30 processors with higher bus width, higher bit width, and of course with higher bit width we will have more advanced architecture and many more advantages. The downside of a 32-bit controller to begin with is that it is more power hungry than 16 or its 16 or 8-bit counterparts, because obviously 32-bit architecture and a more complex architecture would mean it has more components on the die. So if it has more components, it has more transistors, so obviously it is going to pull a lot more power than its 8-bit and 16-bit counterpart. So we have to be aware of that, and cost is also a factor. 8-bit controllers, at least till a few years back, have been much cheaper than their 32-bit counterparts. Now the price range is narrowing, at least for Cortex M4 processors. So, but then again, 8-bit processors are not absolutely getting replaced by 32-bit processors, at least for some time from now to the near future. Moving on, in general, ARM Cortex M processors are regarded as reduced instruction set computing, or RISC. So RISC means it has limited number of very powerful instructions. So it does not have, it is not a CISC, it is a RISC. But nowadays, even whatever you call as a CISC processor, for example, AMD or Intel processors for high-end AMD Intel processors also have, it has a RISC-like architecture internally, and CISC instructions are actually broken up into multiple RISC instructions and fed into that RISC execution unit. So the Cortex M3 M4 processors are based on the ARM v7m architecture, and this implements a programmer's model designed for low latency interrupt processing. So ARM v7m, that is the architecture that we are going to study. So Cortex M4 has ARM v7m architecture, implements a programmer's model designed for low latency interrupt processing with hardware stacking of registers and support for writing interrupt handlers in high-level languages. Now, this is something that we will repeatedly see in the course, and we have dealt with it in depth. That is, in Cortex M, you can actually write your entire code, including startup and all the code in high-level languages. You can write them in C with little bits and pieces of maybe assembly code in the middle somewhere. But apart from that, most of the code can be written in C. And this is a variant of the thumb instruction set we call as thumb 2. Now, the ARM architecture supports implementations across a wide range of performance points. The architectural simplicity of ARM processors leads to a very small implementation, and devices can have very low power consumption. Now, this is a pretty subjective topic to discuss. So when you talk about low power consumption, that is what is touted as ARM's strength, and because with respect to their 32-bit counterparts, that is other processors or other microcontrollers which are 32 bits, ARM relatively consumes much less power. Okay, so because it has a lot of provisions by which you can reduce the power consumption. So ARM has paid special attention in designing a lot of features which can lower power consumption. That is, you can turn off the clocks to different components of ARM. This processor can go into a deep sleep mode where maybe a very small portion of the processor is actually active and the rest of it is not powered down, but it is consuming minimum power. So we have a slide on talking about the different features for low power consumption. So we'll see that. So these are the key attributes, which is why ARM processor is so popular.